All right, so let's go ahead and do a quick review of grams, moles, and atoms. We also learned about molecules and formula units with this concept as well. But just to give you a quick reminder, let's say we had 88 grams of carbon dioxide, and we wanted to know how many molecules of carbon dioxide we wanted or how many molecules of carbon dioxide that is. What we can do is we can take the grams, convert them to moles, and then go from moles to molecules. And so this is going to end up being a two-fraction problem. We put grams on the bottom to cancel out the grams, and we're going to go from grams to moles. And if we were to stop here, we would have successfully converted to moles. But if we're wanting to figure out the molecules, we then will go one more step and put moles on the bottom to cancel out the moles and go to molecules. And if you remember, up until this point, we've always put a 1 in front of moles, although today that's changing. But for now, we'll just stick to what we learned before. We put a 1 in front of moles. When we go between moles and molecules, we use Avogadro's number, which is 6.02 times 10 to the 23rd. And then when we go between grams and moles, we use the molar mass, which we find from the periodic table. Carbon is about 12. Oxygen's about 16, but it's not just CO, it's CO2, so we multiply the oxygen times 2. And when you add all of this together, you end up getting 44. And so you end up with this situation, and if you were to type this in your calculator, you get something like this. Molecules of CO2. We're going to take this concept and expand on it and use this concept with chemical reactions. This unit the concept in this unit is called stoichiometry. And so we're going to learn what stoichiometry is today. And stoichiometry involves the study of the relationship between reactants and products. In a chemical reaction. And the equation that is describing the reaction must be balanced. Okay, so it's very important, must be balanced. And after you balance the chemical reaction, the coefficients in a chemical reaction can describe individual molecules, or it can describe amounts in moles of the product and reactant. And so this is really what we're going to focus on. We're going to focus on thinking about these coefficients here as representing moles. And essentially, when we have this balanced chemical equation here, and there's a 2, a 1, and a 2 here, what this means is that 2 moles of this will react with 1 mole of this, and it will produce 2 moles of the water. And so, again, we're going to think of these coefficients as not just 2 hydrogen molecules, but 2 moles of hydrogen. And so, how many moles are represented in this chemical equation? 2. There's 1 mole of oxygen gas and 2 moles of water. And what these are actually called mole-to-mole ratios. They're called mole-to-mole ratio. And a mole ratio is a conversion factor that relates the amounts in moles of any 2 substances within a chemical reaction. And so let's talk about what are the mole ratios in this situation. Well, we know that 2 moles of hydrogen gas is equivalent to 1 mole of oxygen gas. So here's one example of a mole ratio. Here's another example that 1 mole of oxygen gas is equivalent to 2 moles of water. And then we can even do 2 moles of hydrogen gas is equivalent to 2 moles of water. And so this is the key concept here, is that 2 moles of this is equivalent to 1 mole of that. 2 moles of the H2 will react with 1 mole of the O2. And so we're going to eventually get to the point where, well, what if we had 4 moles of this? What if we had 4 moles of H2? How many moles of oxygen gas would we need? Well, this is a 2-to-1 ratio. And so if we had 4 moles of this and it's a 2-to-1 ratio, that means we would need 2 moles of this. And we would produce 4 moles of that. So let's go ahead and take a look here. This is the stoichiometry mole map. And this here, if you take a look, is actually the grams to moles to molecules that we have been doing this entire time. So is this here. And so this also is the grams to moles to molecules. And so notice how what I just circled there represents what we've been doing this whole time, where we go from grams to moles to molecules. The only new part in this is this middle part here, where we can go from moles of substance A and convert it to moles of substance B. This here is the part that we're going to learn today. So this other parts, these are not different. So these are not different. It's just this here that we're going to talk about today. So let's go ahead and talk about this. So let's read what's happening here. So in the combustion of methane gas with oxygen gas, carbon dioxide and water vapor are the only products that are produced. And the question is, how many moles of water vapor are produced upon the combustion of 4 moles of methane gas? Before you do anything, what you need to first do is write a balanced chemical equation. As you can see, this is the balanced chemical equation for the reaction above. Now the question is, if we have 4 moles of this methane, which methane gas is CH4, the question is, how many moles of this are produced? And I hope you see that the answer is going to be 8, because this is a 1-to-2 ratio. But let's go ahead and write it out to where we can learn how to set this up. And the way you set this up is just like how we set up the mole problems before. Step 1 is to write what's given to you. We are given 4 moles of methane. This is where it's going to be very important for us to be writing not just moles, but moles of methane, because we're going to go from moles of methane to moles of water, and we want to make sure we're keeping track of what substance we're dealing with. So we're starting, in this situation, we're starting with substance A, moles of A. And what it's asking for is moles of B. And so notice the flow chart up here. Can we go directly from moles of A to moles B? And the answer is yes, we can. We can go directly between the two. And so what we're going to do is we're going to set up a conversion, and we're going to put moles of methane on the bottom, because again, whatever is here will always go on the bottom. And we're going to go from moles of A to moles of B, which is moles of methane to moles of water. So notice how these moles of methane cancel out. Now here's the important part to really listen to right now. What always goes in front of moles? Well, a 1 has always gone in front of moles, except now what we're going to do is, this is what we're going to say. We're going to say a 1 goes in front of mole, except when it's mole over mole. If we have mole over mole, what we want to use is the coefficients from the balanced chemical equation. And so there's coefficients here that we use to put into this. So let's go ahead and take a look. So this is moles of methane. And so what is the coefficient for methane? It's a 1. This is moles of water. What's the coefficient for the water? A 2. And so now that we've put this in, we just type this into our calculator, and we get 8 moles of water. And so if you have 4 moles of methane, it will produce 8 moles of water. And this is our answer. Also, we put a smiley face because we're happy that we're back to doing some mathy stuff. All right, next one. All right. In a spacecraft, the carbon dioxide exhaled by astronauts can be removed by its reaction with lithium hydroxide. How many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide, which is the average amount exhaled by a person each day? So again, the first thing we need to do is write a balanced chemical equation. if you take a look, here is the chemical equation. This is something that we have not talked about how to determine per se, but this particular chemical reaction is not one that you'll necessarily see on an exam or anything like that. And really, the only thing you need to balance it is to put a 2 there. Put a 2 there, it is balanced. All right. So now that we have this balanced chemical equation, what we can do is we are given moles of carbon dioxide. And so we're starting with moles of A. And so again, we're given moles of carbon dioxide, and it's asking how many moles of this are needed to react with the 20 moles of carbon dioxide. And I hope you see the answer is going to be 40. But again, we're given moles of A, and it's asking for moles of B, and the question is, can we go directly between moles of A and moles of B? The answer is yes. So step 1 is write what you have. We have 20.0 moles of carbon dioxide. We then are going to go from moles of carbon dioxide, moles of A, to moles of the lithium hydroxide. And again, a 1 typically has gone in front of moles, except when it's mole to mole, we use the coefficients from the balanced chemical equation. And the coefficient for carbon dioxide is 1. The coefficient for lithium hydroxide is 2. And so we type this into our calculator, and we end up getting 40.0 moles of lithium hydroxide. Now, notice how the moles of carbon dioxide cancel out and that we're left with this. Now, something that I really want to emphasize is that it is really important that you're writing the substance here, because can you imagine not writing this substance here and trying to put these coefficients here? It's a lot easier to make a mistake. Also, let's go ahead and put our smiley face. There we go. Okay, next one. This is the decomposition of potassium chlorate upon heating is used as a source of oxygen in the laboratory. Potassium chloride is the only other product, and the question is how many moles of potassium chlorate are needed to produce 15 moles of oxygen. And so again, we have to write a balanced chemical equation, and this is one that we actually can do. So it's potassium chlorate, and it goes through decomposition to produce potassium chloride and oxygen gas. And to balance this, you need to put a 2 here, a 3 here, and a 2 here. And the question is, how many moles of potassium chlorate, okay, so we're looking for moles of this, are needed to produce 15 moles of this. So this is kind of our setup. And so again, we're given moles of A, and it's asking for moles of B. And again, we can go directly from moles of A to moles of B. And so we have 15.0 moles of O2, and we're going to go from moles of O2 to moles of KClO3. And we use the coefficients from the balanced chemical equation. Oxygen gets a 3, the potassium chlorate gets a 2, and so this ends up being 10 moles, and it's 10.0 moles with correct sig figs of potassium chlorate. So this concept really is not too bad. We're using a balanced chemical equation, and the coefficients represent moles. And so this is 2 moles of this will produce 2 moles of this and 3 moles of this. And so we're using those molar ratios to go from moles of one substance to moles of another. And you can notice how this particular problem is asking us how many moles of reactant we need to produce that many moles of oxygen gas. So this one's asking for moles of reactant. Notice how this one's also asking for moles of reactant to react with another reactant. This one is asking how many moles of product are being produced. And so you have a wide range of different types of answers you can ask, or questions you can ask, and it's really the same thing for all of them. It's just looking at the balanced chemical equation and then going from moles of A to moles of B. So it's really not that bad. and we'll practice this a lot, and you'll see that it's really straightforward. All right, that's all I have for you. Have a great day. See you in class.